quick. يلا. Okay.
كيف معاك البيبر؟ لما نجتمع مع إيريك حنقول له إنه خلصنا البيبر ولا إيش حنقول له؟
Off the record. No, I think I finished the control. I just need a few more hours and it should be done. Control section. And then I will take a look at what you wrote for experiments.
You already done all this.
And the simulation, there's just a teeny tiny part. No, teeny tiny? Not teeny. Just a part where we're gonna do the simulation,
All right.
and I
Then
will
we'll
ask
start.
you to make the same plots as the experiments. And I think that should be
You
it.
can get also logs file from the single. Okay, good.
All right, we're going to start. Bismillah. Imagine we have a rod, okay? And we have a mass connected with a cable, okay? And we push that mass, and we're trying to calculate what time it will hit the pole. It's a game that kids play. It's called Tetherball, okay?
No, not again.
You have a rod, okay? And you have a mass connected by a cable. And you push that mass, and it will rotate around the rod until it hits. So it's a game that people play. The first person that hits the rod will win the game.
Not in Saudi.
Yes, kids play it.
So the mass is connected to the rod with a string?
Yes. So the string will shrink with time, so we can.
It's,
Actually
have,
through the
have you watched Recess? No, Gilles Space Tune.
So
It was on Space Tune. They play that in the schoolyard. It's like a stick and then
Yes.
you hit the wall and it rotates around the screen. And it
the
eventually-
motion is this way
Okay.
until the mass
I've
hits
never
the.
seen it. I've seen it
it's
in
the rod.
cartoons.
Okay. So what is the first step when we're doing any dynamics problem?
So free body diagram.
Before that,
Free body diagram. This is the first thing you do when you dynamics problem.
that's 1.2. What's 1.1 or 1.0?
You draw the forces. No, that's a free body diagram.
Allah, you guys are reference frames, huh? Reference frames.
Reference.
But that's part of.
Free body diagram.
We're
So-
terrible students. I'm sorry.
So we have that's the inertial reference frame that's fixed in the rod. And since we have two bodies, we need two reference frames. So we need another reference frame for this, for the rod, for the string. What is the best reference frame choice for the type of motion that we have?
Circular.
Polar, right?
Polar.
Yes. How would those unit vectors look like? If you imagine,
And Z.
if you imagine this is angle theta, where should I put the unit vectors, the polar unit vectors? So this is an easy one, right? ER, right? E theta is in which direction? Perpendicular to, right? E theta. And it's in the direction of increasing theta. Okay. We can start labeling. This is
That's fine. I'm a bit confused. Was it connected? Like, shouldn't the string be connected to the center of the ball?
no, it's connected to the side of the rod. So you can imagine that this is point O, the origin is O prime. So it's connected to the surface, the outside surface of the rod. Okay. We need a position vector to characterize the mass. So this is R. We're ending at P, starting from O. This will give us all the dynamics when we derive this, or when we take the derivative of the RPO. Will give us the velocity, will give us the acceleration, then we can use Newton's second law. So this is the length. And what do we have? We have another vector here. R O prime O, right? We have vector here called R P O prime. We might use that later, we'll see. So let's, so what is RPO? Yes, what is RPO prime? Can someone tell me? Should be very easy. From this point to that point.
So RP minus RO prime?
Yes, from this point to this point. What is this vector?
Yeah, RP minus RO. Like vector O prime P.
No, I want something, let's say, in the ER direction. What is this?
ER.
L, right? Length. And what is RPO? RPO, we know that it's the RO prime O plus RP respect to O prime, right?
In which coordinate?
This vector. We can express it as this plus this,
Position.
right? What do we have? If we know that the radius of the rod is R, can someone give me the components of this vector?
R multiplied by R.
So what is this vector?
R.
RO.
It's in the E theta direction, right? And what's the value? If this is R,
Radius.
The radius R.
the radius. The radius.
So your R is
Minus what? Minus R, right? So minus R in the E theta direction, because E theta is increasing this way, going in the other direction. Plus, we have this already, plus L ER. Okay. So our question is, what is the length as a function of time? Right? And what is theta as a function of time? Because the length of this thing is decreasing, right? As this thing rotates and we have a fixed length. Okay, so initially, if you freeze time, it always helps to freeze time and analyze kinematics. So if you have the mass here, that's at theta equals 0. Okay, after some time, if we have rotation and the cable gets shorter, let's call this L. We are rotating. What is this distance? R times what?
it's like the R multiplied by theta. And
Yes. Yes. So R times theta. So we can get an expression, right? We know that L plus R theta is equal to what? The initial length, right? Now we can get an expression for get an expression for L minus R theta. Make sense?
There's one thing still makes me uncomfortable. Like,
What is it?
So this is not a non-elastic spring, right? String, right?
I mean, it's a cable.
A cable, yeah. But I mean, it could be like this, but this is like in practice, like when they actually hit it, it's always gonna be like this or like this.
Yeah, but if you imagine the string is attached to one point, right?
Yeah, but in
On the
practice, when you actually hit it, it's gonna like the equilibrium is not gonna look like that.
That's
Or-
not equilibrium. That's the initial.
Or like
That's T zero.
yeah, yeah, but when you hit it, it's not gonna be like that.
It's gonna be like that. Like the point is still gonna be fixed there, and the mass is gonna rotate, and the cable will start shrinking. No.
Yeah, but it's gonna be like this. That's all I'm saying.
Alas, we'll get back to it later.
But this keeps it more. I get why you're doing it that way. It keeps it more general.
I'm not sure what you mean by this, so let's catch later, yani.
Yeah,
Okay.
but this is more general.
Yeah.
Yeah.
So as it
I know
rotates,
what he means with this.
what is it?
It's like he's talking about are you pushing it in a vertical, horizontal, like
Give him the mic,
horizontal
Bilal.
plane or like two planes?
We're looking at we're looking at a plane. We're looking at a plane.
Yeah, one plane.
Yes, in
Not two
2D.
planes.
We're looking at a plane in
So he
2D.
was talking about like if you have two planes.
You're talking about 3D situation?
صح?
No. All I'm saying is that it just doesn't make sense to me to. It's fine. Keep going. Keep
Okay.
going.
To meet one.
It just makes me uncomfortable. Because the string has to be at the center. If you're actually hitting the ball, is gonna be at the center.
Correct.
If it's actually moving.
Your theta is bounded. Do you keep theta between 0 and 5?
No.
No, so you allow it to
Theta is
go in
radians.
any rotation.
It's radians, so it keeps on going. So we can plug L here. We have negative R E theta plus L minus R theta ER, right? Just plugging this in here. Now let's take the derivative to get the velocity. The inertial derivative of PO is equal. Inertial derivative because that's what will go into Newton's second law. Okay? Let's superimpose the two frames together to have an idea. I need the red. So we have EX here, EY, ER, E theta, this is theta. When we're doing dynamics, all we care about is the reference frames. How do they move? And how do they rotate with respect to each other? Because once you get that equation or once you get that relationship, you can do anything. Because the second frame is the body frame connected to the rod. It moves with it. So the frame is actually rotating in space with respect to the inertial frame. Once we get that relationship, we can express the dynamics. So, and for us to do that, we need to get an expression for the rotational velocity, omega, of that frame. So the frame is rotating with a certain angular velocity with respect to the I frame. That's how you say it. So the rotational velocity of B frame with respect to the I frame. What is this expression as a vector? So that's correct. It's in the E3 direction because we're rotating about this axis, right? And what is the value? The velocity, if this is theta. Yes. theta dot so this is necessarily not constant because the tether is shrinking. Okay, so it's a function of time. So now let's derive the velocity. So that's the inertial derivative. It's going to give us the inertial velocity of p with respect to O. Let's check your product rule. So what do? We're taking the derivative of this. R is changing or no? The rod is not changing, right? Negative R. You take the inertial derivative of E theta, right? So derivative of the first plus derivative of the second, 0 plus the derivative of the E theta.
No. The first multiplied by the derivative of the second plus
Yes.
the second
Yeah.
multiplied by the derivative of the first.
The derivative of the first is constant, 0. So plus minus the derivative of the second. So that vector E theta is changing, right? Okay. So what do we have? Plus, I need your help, guys. Yalla. Let's take the derivative of this.
Negative r theta dot.
Nice. Okay, skipping ahead. So negative r theta dot. In what direction?
E theta. ER.
ER. ER. Plus. كمل استمر.
It's also minus. Minus r theta der dt. Oh no, it's L minus r theta.
Yes. So it's the inertial derivative of the ER L minus R theta, right? So how do we get this? And how do we get this? From the last session? Transport theorem. Do you remember?
You're the best student here.
When you are taking the derivative of a vector, you should always use something called the transport theorem. Some people call it a different name. I like to call it the transport theorem.
I respect to E, then derivative of E respect to T.
Transport theorem. Same thing here. So, the transport theorem says what? Let me write it. Why should I write it?
It's transport or like chain rule.
No, it says transport. It's called transport theorem. Not related to the chain rule at all.
So the dynamics thing.
Yes, so if you have two bodies, let me draw it here actually. Just keeps on moving. Is there a way to fix it? Okay. So if you have
Who was here yesterday?
the inertial derivative of a certain vector, okay, I would just call it a vector. You take the body derivative of that vector plus the angular velocity of the body reference frame cross the position of that vector. This is the transport theorem. Dissect it, look at it, make sure it makes sense to you. So if you have a vector, let's say this is our vector, and we have reference frame EX,
Can you re-explain this?
yes, EY. We have a reference frame here, ER, E theta.
I tend to
If I want to take the inertial derivative of this vector, okay, with respect to the inertial frame, I apply this formula. I take the derivative of the vector with respect to its coordinates. So if the vector is shrinking or, expanding, plus that reference frame's angular velocity with respect to the inertial frame, cross product with the R, with the position vector. It might make more sense now.
So you're changing the derivative of the frame. So you're changing from one frame to another?
Yes, because I need to get the inertial derivative with respect to the I frame. Let me just keep going here. It might make more sense now. So the R in the body frame, okay, is that changing? Like the length of the rod, is it changing? So this term should go to 0 in our case here. So we have negative R. What do we have now? We have the inertial, the angular velocity. We just apply the formula. Okay? What is it? Actually, let's substitute. I have theta dot E3 crossed with what is the E theta? Make sense?
No, I have to go.
Have to go? Okay. Negative R theta dot. Let's do another transport theorem here. Actually, here's ER plus I omega B crossed with ER L minus R theta. So negative R what is the cross product of this, guys? So E3 so E3 crossed with E theta. So E3 is going out of the page, right? Crossed with E theta, or no? E3 crossed with E theta, negative ER. So negative plus ER. What do we have here? That's theta dot E3. E3 cross ER. E3 cross ER, negative theta, right? Oh, theta. Theta. So we have negative R theta dot ER plus L minus R theta theta dot E theta. These two will cancel, luckily. So we're left with L minus R theta theta dot E theta. So now we have an expression for the velocity. This is the inertial velocity of P with respect to O. We need a bigger board, but let's erase this now. Now take another derivative, inertial derivative of the velocity is equal to what? Derivative of velocity,
Acceleration.
acceleration, inertial acceleration, which later will equal to what? Total force times the mass, right? So this will test your transport theorem once again. So we have d dt
Divided by mass or times mass?
divided, right? Force equals ma, yeah. Thank you. F divided by mass, right? Correct. So the initial derivative of that thing, again, product rule. L minus R theta, theta dot E theta direction, plus L minus R theta, theta dot inertial derivative of E theta. Right? We only have one transport theorem here. Can someone tell me what this will be? Again, it's the P crossed with E theta. What is this? Theta dot E3, right? Cross with E theta. Good? Continuing on. What's the derivative of this thing with respect to time? Calculus, guys, yalla. Minus R theta dot squared, correct? Plus L minus R theta, theta double dot. MashaAllah, good. Okay. In which direction? E theta. This thing, so E3 crossed with E theta, negative ER, right? Yeah. So what do we have? So we have negative R plus L minus collecting terms, E theta minus L minus R theta, theta dot squared ER. Almost there, guys. We are done. Yani. So now what do we apply? Now we have the acceleration. What do we do? An idea how to proceed, guys?
What do you want to do?
So we want to get a function of theta dot, or theta with respect to time. So after getting the acceleration, what can we use to relate the forces and Newton's second law, right? So we know that the mass times the initial acceleration is equal to the sum of forces on the point P. Now let's draw the free body diagram. So imagine this is point O prime. This is the mass, point P. What forces do we have?
mass and what's it called, tension from the string.
Oh, you mean weight?
Yeah.
There's no weight. We're considering the plane just in 2D. So just
So
tension.
the tension from the string.
Yes. How would you quantify this vector?
Good question. It has to oppose.
So in which direction and what magnitude does it have?
Direction is along the string.
Yes, which is what?
Towards the pole, towards P.
In terms of unit vectors?
You were using, I forgot the
ER.
ER.
Yes. That's the force. So now let's plug that into Newton's second law. So we have the mass, there's the acceleration. Let me just go ahead and plug everything directly here. So we have an expression for theta. So we have mass times this thing. Is equal to what? Negative t in the ER direction. So we have the ER components. Now we need the E theta. Is there something in the E theta? So there's an implied 0 in the E theta. So now we have the equation for theta, or theta double dot. We can write the components of E theta as r theta dot squared plus L minus r theta dot is equal to 0, right? Now isolate for theta double dot equal to r theta dot squared over L minus r theta. خلاص, you're done. This is what is this equation? I want an answer from you.
I'm just learning.
Theta double dot with time. Remember anything with the ODEs? Differential equations?
Second order.
So second order. كمل.
Second order
Linear, non-linear.
Yeah, it's non-linear.
It's not linear.
Why?
Why? Because the theta dot is divided by the theta.
لا. Is theta dot squared.
Squared also, yes.
Or actually that's correct because we have a theta in the fraction, صح? So now you can rewrite it. I will just give you guys the setup to solve it. So you can rewrite it this way. L minus r theta, theta dot squared. So now this is ready for some math magic you can do to solve. You can use, what is it called? This is of the particular form, y double dot is equal to a function of y times a function of y dot. And you can solve it to get theta in terms of time.
Done?
Sure about
Spring
it.
can solve it.
Thank you guys.
he did not consider the twist that will happen more as you push it because it's connected from the side.
Twist. Yeah, I think that's
If it's not
why.
connected from the middle, then you will have some
Yeah, I think that's
moment.
why.